Hello, Heretik here. Now, from our last discussion about why we should consider a particle like this simulated proton as a moving field instead of a point source, we're now going to apply that data and use it to show how wave-particle duality experiments occur. Now, if you didn't watch the last episode, I would strongly recommend that you do so, because for many people, they will not understand unless they see that first. In any event, let me go ahead and start. So, if this were a proton and it were moving, the way it interacts with things can be seen in two ways. The most obvious of which is if this proton is moving and runs into a solid object directly. Now, we call that particle interaction. It hits as a particle, it simply strikes the target. No deviation, no movement, left or right. Whatever pattern it was moving in will show up at the target. That's rather straightforward, and that's what early scientists expected in all cases. But then they went and they performed a double slit experiment, similar to the ones they did with light waves, with a stream of protons, and something very different happened. Let's take a look.
Now what is seen here is the observed experiment that led to the discussion of particles behaving as waves. This is the infamous double slit experiment. In this case, we sent a stream of particles, either protons or electrons, and we hit them with a double slit grating. When they hit the grating, at the aperture points, the open spots in the grating, each aperture spot changes the flow from a straight particle stream into a spherical point source. Those two point sources then interfered and show up on a screen as light and dark sections, just like light would behave going through the double grating. And this is the behavior that we're expecting to prove through theory. From the previous lecture, a moving charged particle, either a proton or an electron, will have what I call an electromagnetic cloak of moving fluxes and electric fields that correspond with having the electric field surrounding the particle moving with the proper application of Maxwell's equations, namely Faraday's law and Ampere's law. So that a moving particle, as seen from a third party, would see the representation you see in front of you instead of just a single particle. Now let's take a look at how these particles react as they are moving through a single slit. The first set of particles are all protons. They're moving at a velocity. And of course, please get past my drawing ability, but these protons are all moving in a single group, in a single direction. And because they're all moving the same, none of them are moving in relation to each other, thus none of them see the electromagnetic cloak occur. But let's see what happens as they approach the slit. See, the electrons that are on the outer shell of the metal of the slit are also moving in a circular fashion. And at the edges of that particular slit, the protons that are on that edge are first encountering the electromagnetic tails from the electrons. And if you notice, our initial group of protons are somewhat randomly scattered, but still moving in the same direction. But the proton's electromagnetic field around the proton is starting to encounter the cloaking effect from the moving electrons. Now, let's take a closer look of what this really causes. As the electron's moving, it has its cloak, and that cloak starts to brush aside the proton's electromagnetic field. Once that happens, the electromagnetic field will cause the very first edge proton to turn slightly, in effect dealing with the running over of the field. The other protons are still moving in the direction that they were at initially. The next effect that occurs is that the first proton that has turned is now observable to the other protons as having the electromagnetic cloak of itself, because now its motion is a different direction and thus is seen as moving separately. And this continues for each subsequent proton in each rank. They will eventually turn and generate their own cloak. Now let's look at the whole effect as it occurs. As the first, if you take a look at the lower right proton, it first comes in and meets with the blue line, which symbolizes the electron's cloak. It brushes against it and turns slightly. As it continues to brush against it, it turns more and more. And if you watch its progression along the base, it eventually gets to a perpendicular point and will be released perpendicular to the opening of that slit, shown by the golden area. But as it gets approximately 2 or 3 steps into the process, its cloak has moved substantially enough so that the next rank of protons are brushing against that cloak. And that is also acting like the electron's cloak did to start to steer the particle. And then several more further down, the 3rd rank, and further the 4th rank, 5th rank, etc. All will eventually turn and start moving in a direction different from its original direction due to the cloaking force, or cloaking effect, and the particle's electromagnetic field crossing it and steering it. Now what this eventually leads to is a twofold solution. At the particular point in the sequence, it does turn the proton, and depending upon how close it is to the initial position along the wall, it will turn more or less, depending upon what we just saw in the last discussion. But something else also happens, is that the electromagnetic cloaks also create bands of area where the electromagnetic field is stronger or weaker, which leads to the particles organizing in a way that is, you'll have a band of particles because it has a strong field effect. Then you'll have an empty section. Then you'll have a strong section. And it goes back and forth just like you would have with an electromagnetic wave, because it is a wave. It is a wave of a spectrum of those particular cloak waves built in a cross arc across the whole gap. So as it exits the slit, two things happen. You have particles all leaving as if from a point source, and it has a specific wavelength determined by the width of the slit and the velocity of the protons. Now, when you take both of those slit solutions together, you get exactly as the experimental value by having two interfering point sources with specific frequencies of particles, leading to, on this experiment, having areas that are an interference pattern with areas of lots of particles, no particles, lots of particles, etc. And thus, this is how we observe wave-particle duality due to the cloaking effect of the particle's motion in classical physics.
The open aperture of that slit, they're combined in a semi-random fashion, but all moving with the same velocity. So after seeing how that experiment took place and how the model of the moving particle causing its own electromagnetic cloak wave contributed to that result, that we now have shown how the theory of that cloak wave actually causes those optical factors to take place. But we're not quite done. See, the goal here is to understand the duality nature. And let me say that I will use this as the particle nature and this as the wave nature. Now, physicists, especially in the field of quantum mechanics, declare that it is either one or the other. It cannot be both. It must not be both. Well, that's just bad human logic. Because we have shown that the same particle will either act in a collision sense as a particle, or as it moves by something, act as a wave. Yet the same particle shows both behaviors. Now, I've seen many articles where they use the word choose or decides, or, well, one, it can't decide or choose or do anything else. The actual truth that I have shown is that it is both a particle and a wave all the time. Let me state that again. It's always a particle and a wave. It depends upon how the interaction with that component takes place. See, with a collision, you're not dealing with the electromagnetic tail at all. You're dealing with the physical particle. And either it hits with a direct blow or a glancing blow, it's still the particle and its initial segment of its electric field. That's all that happens in the interaction, and thus acts as a particle. But in the wave condition, it is actually the electromagnetic tail that is the wake of the particle's motion through time and space that is causing the detected abnormalities in its motion, which we call the wave equation, the wave function of that particle. Both conditions exist simultaneously all the time with a moving charged particle. Always. And that's what quantum mechanics cannot understand, is that something has two traits, and how we interact with it determines what trait we see. I hope you found this discussion useful. Our next discussion is how this phenomenon that we have just covered leads to the formation of hydrogen. Thank you.